we looked at the basic properties of waves and how they behave in terms of what affects wave speed. Now we're going to look at superposition, so what happens when waves meet. What the principle of superposition tells us is that when two or waves are simultaneously present at a single point in space, the displacement of the medium at that point is the sum of the displacement due to each individual wave. So in other words, when two waves are going to meet, they're going to be in the same place at the same time. They're going to have either greater amplitude or less amplitude depending on what the two waves looked like. And this will make more sense once we see a picture. And what this is called is actually interference. So interference is the superposition of two waves. Think of it like the sum of two waves when they're meeting. There are two types of interference. The first is constructive interference, and that's when both waves are either positive or negative, so they both have to be the same. So either both positive or both negative, and the total displacement of the medium is larger than it would be for either wave separately. So what we have here is wave 1 and wave 2. When they combine and meet, if they both have an amplitude of x, then their amplitude for the superimposed wave will be 2x, because this added to that. So if you want to look at this with numbers, let's say this was 1 meter and this was 1 meter, then this amplitude would be 2 meters. And then down here would be the negative 2 meters. So you can see how these two waves added together constructively to give you a resultant that was greater than it was before. The second type of interference is destructive interference. It's the complete opposite of constructive interference. And this is when the waves are opposite. So one's positive, one's negative. Where they meet, they're going to cancel out or be less than what they were before. So in this case, this was positive x, this was negative x minus x equals 0. So the resultant would be waves that were completely canceled out. And these were two perfect examples. So you may have situations where they're not equal amplitudes, and in that case, it'll look different. So it's not completely canceling out, it's not completely adding, but it would be a mix of the two. So in order to use superposition, you need to know the displacement of each wave. So you're looking for the amplitude, and then you're going to go through, and it's a little bit tedious, but you need to go through point by point and add the displacements to figure out what the superposition or the sum of the waves would be. So again, this is tedious, but it's not terribly difficult. I'll do two examples. Okay, so we have two wave pulses on a string approaching each other at a speed of 1 meter per second. How does the string look at t equals 3 seconds? So I'm going to redraw this and try and space this out as evenly as possible. So these are the distances. Okay, and we can assume that each wave is moving well, not assume, but we know that each wave is moving 1 meter each second. So if at 0 seconds this was the position, so this is the position at 0 seconds, in 3 seconds it'll be over here. So I'm going to redraw that wave here. So the triangle moved to the right at 3 meters per second. At 3 seconds, that would be that wave's position. The rectangle was moving to the left at 3 meters per second. So after 3 seconds, it would have moved 3 meters. So the rectangle would be here. These are both positive amplitudes, so they're going to add. It would be constructive interference. So the total wave would look like that. What I drew in purple. All we were doing, they were in the same place at the same time. They constructively interfered. We added that to that. So this shape looks nicer than putting the square on top of the triangle. That would have worked as well. So how does the string look? It looks like that. We'll do one more. So now we have the triangle with a negative amplitude and the rectangle with a positive amplitude. Once again, redrawing this line. Get these all lined up. Okay, so still moving at 1 meter per second. After 3 seconds, we're going to redraw what these look like. So the triangle will be here. The rectangle will be here. So when we add those, what's happening is this is being taken away from the rectangle. So we're going to be left with this shape. What I drew in purple, so it looks like an M. I'll do one more quick example. We have these two waves. It wants to know how the string appears at t equals 2 seconds, so similar to what we just did. This should be x in meters. So 1, 2, 3, 4, 5, 6, 7, 8, 9. After 2 seconds, the rectangle will be here. And the trapezoid will be here. So when we add those, we're going to have negative here. And then these are, I didn't draw it right, but these are equal amplitude. So nothing here. Those are going to cancel out. In other words, this cancels that out. And then here we have this much being taken away from here. So we'll have a wave that looks like that in that general shape. When you're doing these, it does actually help to use different colors. So if you have colored pencils or crayons or colored pens or markers, bring those into class because it'll make a lot more sense if you're looking at these with different colors. So that's really it for superposition. We'll do a bunch of practice with this tomorrow. There's several multiple choice questions I've seen where you need to figure out what a wave looks like at certain times. So we can almost guarantee that something like this will be on the AP test.